Welcome back. In this video, we are going to solve problem 10-92 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic that we are covering is theories of failure. So statement is the shaft consists of solid segment AB and a hollow segment BC, which are rigidly joined by the coupling at B. If the shaft is made from A36 steel, determine the maximum torque T that can be applied according to maximum shear stress theory. Use a factor of safety of 1.5 against yielding. So you can see this is segment of shaft AB and this is of segment of shaft BC that are coupled together using a coupling at B, and there is a torque T applied to this coupled shaft. So you have to find this torque T by using the maximum shear stress theory, and you have to take factor of safety of 1.5 against yielding. Let's start with the solution. As you can see, both the shaft are under pure tension, so I can write that this is a case of pure shear because there is no other load. So this pure shear will cause torsion, and due to this torsion the shear stress will be generated in each shaft. So the shear stress is contributed by torsion. As we have two segments, one is this is shaft AB is solid segment and shaft BC is hollow segment. So we can write that maximum shear stress in hollow segment will be equal to T into C of hollow segment divided by J of hollow segment, and maximum shear stress that will be generated in solid shaft will be equal to T into C of solid divided by J, where C is radius and J is the polar moment of inertia. So Js is polar moment of inertia for solid segment and Jh is the polar moment of inertia for hollow segment. So what we will do is that we will find them. Again, you can see that Ch for hollow segment, you can see the hollow segment is this one. So the outer diameter is 100. So Ch will be equal to 100 divided by 2, and that will be equal to 50 millimeter. So Ch will be equal to 50 millimeter. I will write it, and 50 millimeter is equal to 0.05 meter. Okay, now for Jh, polar moment of inertia of hollow shaft, that we can write formula for this is pi by 2 Ch power 4 minus Ch inner power 4. Okay, so pi by 2, I will put the value pi by 2 C inner Ch, which is the outer radius, that is 50, and that is 0.05 power 4 minus C inner. So inner diameter is given as 80, so that will be radius C inner will be equal to 40, and 40 in meter is 0.04 power 4. And you can calculate that. I will calculate. So this will be equal to 0.05 power 4 minus 0.04 power 4 multiply by pi and divide by 2 will give you this value, which I can see. You can see that it is 0.00000579, and unit will be meter power 4. And we can write this Jh is equal to 5.79 into 10 raised to power minus 6 meter power 4. Okay, now here we will find Js. So solid, for solid shaft, I will check it that radius is diameter is given as 80. So Cs will be equal to 80 divided by 2, that will be equal to 40 millimeter. So I can write Js is equal to 40 millimeter, and in meter Js, sorry, not Js, it is Cs. 40 millimeter. Let me correct it, because CS is the radius of solid shaft, so CS will be equal to 0.04 meter, and JS will be equal to pi by 2 CS power 4. So put the value pi by 2 multiply by 0.04 power 4 will give us JS, and I will calculate it here. 0.04 power 4 multiply by pi divide by 2 will give you 0.00004002 meter, or we can also write JS is 4.02 into 10 raised power minus 6 meter power 4. Now you have each and every value. So what we are going to do is that we will find maximum shear stress for hollow segment, that is T. T is not known, which we are going to find, multiply by CH. So CH is 0.05 divide by J, and J is 5.79 into 10 raised to power minus 6. So what we are going to do is that 0.05 divide by this value 0.00000579, and you can see we will have this 8635.5 times T. Okay, so maximum shear stress in hollow segment or hollow shaft is 8635.5 times T. Now we will find this shear stress in solid segment. So shear stress in maximum shear stress in solid segment is T into C. So T is there. C is 0.04 divided by J, which is 4.02 into 10 raised to power minus 6. And what we will calculate its value. So again you can see 0.04 divided by 4.02 into 10 power minus 6. Okay, and that will give us 9950.2 times T. This is T. Okay, now we have two shear stresses, one for the maximum shear stress in hollow shaft and one is maximum shear stress for solid shaft. So by comparison we can see that by comparison the points on the point or the shaft of solid section will experience larger shear stress. So what we are going to do is that we will select this maximum shear stress in solid segments. Okay, so we will take maximum shear stress in solid segment for calculating this torque value. Clear? Okay, now we have this maximum shear stress here. You can see this is under pure shear stress. So sigma x is equal to sigma y is equal to 0, and we have only shear stress of xy, which is 9950.2 times T. So if I draw the state of stress on the element, so it will be purely like this. This will be the state of stress, this one, and this shear stress of xy is 9950.2 times T. Okay, now we are going to find out principal stresses, because you know that in maximum shear stress theory you will need sigma 1 and sigma 2, which are the principal stresses. So principal stresses sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Since these values are 0, so this term will become 0, and we will have only plus minus under the root. This term will be also 0, and we have only 9950.2t whole square. And when this square root will cut with this square, so we will have two values, plus minus 9950.2t. And from here we can see that one principal stress is 9950.2 times t, and another stress sigma 2 is minus 9950.2 times t. Okay, I will copy these two values because we will need, and we will move toward new page. Okay, I will paste them over here, and you can see here that both sigma 1 and sigma 2 are opposite in sign. So according to when both principal stresses are opposite in sign, so according to maximum shear stress theory, what we will take is that we will take this sigma 1 minus sigma 2 will be equal to allowable shear stress. And since we have been given factor of safety, that factor of safety is given as 1.5, so we know that factor of safety is equal to this yield strength divided by the allowable stress. So from here what we are going to do is that we will calculate this allowable stress will be equal to sigma yield divided by factor of safety. Okay, sigma yield is not given, but material is given, that is A36. So what you are going to do is that you have to go to the end of the book, and in average mechanical property table, that is in SI units, so you can see A36 is 250 megapascal. So I will show you, this is A36, so this is tensile strength, and the unit will be megapascal. So 250 megapascal. So 250 divided by 1.5 will give you allowable stress, and when you calculate it, so 250 divided by 1.5 will give you 166.67 megapascal. So this is the allowable shear stress, and according to the maximum shear stress theory, when sigma 1 and sigma 2 is opposite, so this will be the condition. And you can see that sigma 1 is 9950.2t minus sigma 2 is minus 9950.2t. Clear? That should be equal to allowable shear stress. Okay, so what we are going to do is that this become equal to 9950.2t. This will be plus 9950.2t will be equal to allowable shear stress, and that is 166.67 megapascal. So 9950.2t plus 9950.2t will be equal to sigma allowable, which is 166.67 megapascal, so 10 raised to power 6 pascal. Okay, so 9950.2 plus 9950.2 is actually 19900.4 t will be equal to, this is t, 166.67 into 10 raised to power 6. So from here we will get t will be equal to 166.67 into 10 raised to power 6 divided by 19900.47. So I will write 166.67 multiply by 10 power 3 multiply by 10 power 6 divide by 19900.4, and you can see that torque is equal to 837.1.69, and unit will be Newton into meter. And if you convert it into kilonewton, so it will be equal to 8.37169 kilonewton into meter. And if you round it off, so it will be 8.38 kilonewton into meter. So this is our required torque T that can be applied on this system. And this was all about this problem 610-92. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.